Hello, welcome back to the CMSoft case study of fast simulation of heat transfer using C# and OpenCL. In this video of the video tutorial, we're going to keep on talking about how to create the texture that we are going to display to our user, showing the distribution of temperature in the plane plate. So previously, we saw how to create an OpenGL texture and then retrieve it, and how to use it in OpenCL. So we saw how to share a texture objects from OpenGL to OpenCL. Now we're going to analyze how we transform an intensity value to a color value, and how we're going to implement this using the GPU to set colors to the texture and display the image to the user. So we need an intuitive representation of temperatures of hot and cold to display to our user. So we know that intuitively this region here is hot, and this region here is hot, and the yellow and green is somewhat intermediate, and the blue region here is the cold part of this plate. So since we're controlling the simulation, we can know beforehand what are the maximum and minimum values of the simulation. So we write a function, getColor, that's going to be executed in the GPU itself, that maps intensity values to color values. And that's based on the minimum value and maximum value of temperature. So in a real application, you might not want to calculate the minimum and maximum on the fly every time. And in the GPU, that's even not less practical. So by creating the white as the hottest part of the plate, and this deep blue as the cold part of the plate, we can get a wide variety of color information from here. It's very usual to go just from blue to red without going all the way up to white. So in this code, we go all the way up to white because then we have, let's say, an extra dimension to represent colors. So let's discuss this code a little bit. So this is our function getColor, takes as arguments the maximum value of temperature, the minimum value of temperature, and the temperature, the value I'm trying to classify. So the first thing I'm going to do is get t to the region of agemin to agemax. OpenCL C99 provides us the clamp function that gets the value of gets a given value and maps it to in the region from minimum to maximum. This means that if t is less than agemin, it gets set to agemin, and if it's more than agemax, it gets set to agemax. Well, I could just do this manually. I could input something like if t is less than agemin, t equals agemin, for example. But I don't want to do that because this function is built in the hardware, and so it's very efficient. It's not going to happen that I'm going to write a function that's more efficient than what's provided by the vendor's DLLs. So in this OpenCL editor, which comes with OpenCL template, I put here some common math functions and some common native functions. So it's a good idea to take a look at the OpenCL specification and see what each of these functions do, because while you can still implement them yourself, it's faster to use these functions that are pre-built into OpenCL. For example, we have the multiply add instruction, we have the fused multiply add, maximum, minimum, and lots of other functions. This is our sqrt, that is 1 over the square root of the argument. So it's very interesting to know that these functions exist, because they are much faster than what you could implement yourself. So at this point, I want to map, getting back to our code. At this point, I'm going to map a value of a relation of t to the interval 0, 1. So if t is age min, it gets mapped to 0. If t is age max, it gets mapped to 1. And then I go on and I proceed. If the value is between 0 and 0.2, that's a cold temperature. Then I set 1 as the intensity for the blue component. I leave red as 0. And I set the green component as it goes from 0 to 1, because if this branch is executed, z_rel is less than 0.2, so this can go only up to 1. Now, if the temperature is a little bit higher, from 0.2 to 0.4, I set green to 1, and then I start reducing the blue component. So I'm going to go, in this region, I'm going to go all the way up to green. And then when the temperature exceeds 0.4, that is, it's 40% along the way from the minimum to the maximum temperature, up to 60%, I leave the green at 100% and start to increase the red component. Then in this in the next stage, I leave red at 1.0, 100%, and I start decreasing the green component. So when I'm in the interval of 60 to 80% of the whole interval, the color starts to get red, meaning that the temperature is higher. And finally, if the temperature is greater than 0.8, I set red to 1, and I go up, I turn up the crank, and increase the values of blue and green up to the white color, which corresponds to blue, green, and red with value of 1. And so this is the way that we go about mapping temperatures from intensities to colors, so that we can create a beautiful picture and present to the user a better representation of the temperature distribution in the plate. So now that we have the tools we need to display the results to the user, we're going to go over some considerations of initial values and boundary conditions of the heat equation, and then proceed to simulate the heat transfer equation. Thank you.